The following program is brought to you by Caltech.
Anyway, our last talk of the short courses is we're indeed privileged to have Tom Jones to present to us about human missions to asteroids. That's the motivating factor for much of this workshop, is to talk about human missions and creating a target for human exploration. Tom's biography lists him as a scientist, author, pilot, and then incidentally a former NASA astronaut. He's spent 53 days in space, working in space. He's an integral part of the space station development. He's oscillated in his career between flying on Earth and flying off of Earth with a great deal of experience in aircraft flying as well. And is after leaving NASA, as I said, been an author. His most famous book is Skywalking, which has gotten a lot of attention. His memoir of space, but he's also written a science book of planetology with Ellen Stofan, and remains very active in the whole helping NASA and the Advisory Council in defining the future of human exploration and working with the space explorers on all the questions of asteroids. I guess you've been studying asteroids since you were in graduate school, so you come at this for a long way.
Thanks to Dr. Lewis there.
Okay, so Tom Jones.
Thank you. Thank you, Lou. And I'd like to thank the Keck Institute for inviting me to come to the short course and the study this week. It's an opportunity for me to learn a lot about all the different technology fields that have been discussed today. Also an opportunity to see a lot of old friends here who I haven't seen in a few months or years in some cases. My advisor, John Lewis, is here. I'm really pleased to see him. But it does remind me, though, how long it was since we started working together. And I've got a lot of newer colleagues in the audience, so I'm very glad to be with all of you this week and to have a chance to share ideas. And like I said, I think the bottom line for me is I'll have a great opportunity to learn from you. I'd like to talk briefly today about human exploration and how this study might fit into the schemes that are being discussed for extending human presence beyond low Earth orbit, where we haven't gone in nearly 40 years. And I'll get right into that, I think. But I wish we could design a space program with a clean sheet of paper to accomplish getting out of low Earth orbit and beyond the moon. We can't do that. We're in a real world today, so I'm going to start my talk with some references to the current state of affairs and perhaps where that's leading us and how we would have to change that to realize some of the goals that we have this week. I'll talk about some of the reasons I think we should explore near-Earth objects in conjunction with our other efforts to go into deep space. Talk about some of the current exploration thinking that's been talked about at NASA that I've been able to put my ear to over the last few months and share some of those ideas. Some typical mission profiles for asteroid exploration and some of the considerations and limitations that human explorers will find when they actually get to an object at some point and how they'll be able to deal with solving those exploration challenges, how we'll do field work on an asteroid. I thought there were some very good ideas this morning in terms of anchoring that will have to obviously be greatly expanded and proven before we can use them, but it's a great promising note to start off on. So let me find my pointer remote control. Here we go. We're going to start off with the current state of affairs. I used to fly on the space shuttle. Today, from LAX to here, I took the super shuttle. And the gulf between the space shuttle and the super shuttle is wider than that of the International Space Station and the Wright brothers. So it was just a tremendously exhilarating ride over here from LAX today. Recommend it to all of you. Space shuttle's been retired. And so we are here in 2011 without, in the United States, a way to get to low Earth orbit with people and a way to access the International Space Station. This is the way I saw it when I visited it 10 years ago and helped deliver the United States laboratory, which is still the brains or the nerve center of the space station. So in 10 years, we've gone from this space station to this space station. Great leap in progress in terms of construction complexity and the engineering challenges. This is a remarkable achievement to see the space station as it is today. What worries me is that in 10 years we've gone this far. In 10 more years, will we be able to see anything visible in terms of progress in low Earth orbit or beyond? I have big worries about whether we're going to see anything visible beyond this in 10 years. Nevertheless, there's some hope that we can use this facility, which is presently occupied, at least by 3 people right now, and I hope it'll stay that way and move back to 6 very quickly. There's hope that we can use this facility, I think, at NASA and with its partners for enabling us to go to other destinations in cislunar space and then beyond. And to that extent, the space station just completed in terms of construction is underutilized in terms of exploration technology testing. And I think that's one of the opportunities NASA has, is to greatly expand this facility in terms of human exploration technology, not just basic fundamental research, which was its original purpose. Here's some basic facts about the space station, and you can read them over for yourself, but the football field or soccer field analogy is a good one. It's just an incredibly large and complex space. And with 3 people living aboard right now, they are rattling around like acorns in a tin can. There's not really much chance of you actually running into another human being for hours at a time. They have that much elbow room. So you can be focused on your job up there for several hours and not run into one of your crewmates, especially with only 3 people living in an outpost with a living volume of about a 5-bedroom house. The crew should be 6, and that may be restored if the Russians restore launch access or to low Earth orbit soon. You can't really see this very well, but this is Tracy Caldwell silhouetted against the cupola windows in the space station. And it truly is a magnificent place to live. So my colleagues have told me, those who have spent months up there. And I think we may not use this particular orbit and location for jumping off in terms of transportation, but there is a lot at this facility to offer in terms of knowledge gain and technology testing that can be applied to reaching beyond low Earth orbit. We know that in August, the Russian Soyuz booster failed, delivering a Progress cargo ship to the space station. So that problem has to be solved, and the Russians say they're going to test an unmanned version of the rocket in October and then hope to resume human launches in late November, and then getting the crew size on the space station back up to 6. The Soyuz that's at the station right now has a shelf life of 6 months or so, about 7 months actually. And so they could stay up there conceivably till 7 months expire, December. But the days get so short in Kazakhstan and the weather gets so bitter at the landing site that they'll probably bring the crew home in late November. And if the launch capability isn't restored, then the space station will be demanned or decrewed for the first time in over 10 years. And that's bad from a record-keeping point of view, but it's also bad for the space station. There's a risk involved in having nobody aboard the space station to deal with problems which do crop up on a regular basis. And most of the time, they're a very simple fix: a computer reboot, some kind of reconfiguration of coolant lines, that sort of thing. Something serious happens, though, and there's no crew aboard. The station can't deal with that underground control, and we could risk having the station go out of control, and we could lose our investment up there if we had a cascade of serious failures. But we'd like to see the Soyuz return to flight very quickly. It is the only way that American astronauts can get to the space station until commercial companies take over here. So you have the landings in Kazakhstan, as I mentioned. Hopefully before the winter gets too bitter, we'll be able to see the current 3-member crew come home, but by then be replaced by an oncoming expedition. Of course, NASA is working very loudly and publicly, talking about how they're going in the direction of commercial spaceflight. And I think the commercial companies like the Falcon 9 from SpaceX and the Taurus 2 from Orbital Sciences in the near term will deliver cargo. Probably within the next 6 months, we'll see the first cargo delivery from the Falcon 9. And then eventually, these companies and others hope to move on to crew transportation. The Dragon capsule from SpaceX, this is the Boeing's, I think it's the CTS, as I recall, 100, which is a 6-person crew transport married to an Atlas V. This could be another reliable system. So NASA will sift through these bids and concepts and hopefully restore American-based transportation to the station. So we have a redundant way to get to low Earth orbit and to protect that investment up there. And then at the same time, NASA is developing the multi-purpose crew vehicle that used to be called Orion. I guess it still is. But structural test articles have been built. It's been dropped out of it's been dropped in parachute tests. It's been rocketed off the launch pad for pad abort tests. It's been dropped into swimming pools for splashdown tests. So it's coming along. And sometime in the latter half of this decade, it'll probably make an orbital test flight with the crew aboard on some small rocket. And then eventually, as you heard about 10 days ago, NASA is going to fly it atop the Space Launch System. The stats on this vehicle are that in the initial version in 2017, so they say, we'll have about 10% more thrust at liftoff than the Saturn V that Rusty flew. And then the upgraded version, up to 130 metric tons of orbiting payload, will have about 20% more thrust than the Saturn V. So when the larger version of this rocket flies, if it does, then we'll have a truly great lift capability. Whether this is the right solution for getting out of low Earth orbit is another question, and whether or not it can survive all the budget wars before it makes its first flight, I think is a bigger question than the technical abilities of the rocket. We'd like to go beyond where the Apollo guys went with the moon, and so we look out into the inner solar system. So Mercury, Venus, and like Bill Ayler showed us, we've got Earth moving through a shooting gallery of near-Earth objects in the inner solar system. And of course, they come close to us, and so naturally we think about visiting those as well as visiting the moon with a heavy lift launch system and a deep space craft. There's a whole zoo of objects out there, but I like this slide that the Planetary Society put together because we have main belt objects like Lutetia, but here is Eros, the largest near-Earth object, and just to remind us what we're shooting for, this is Itokawa, 500 meters across. So in the zoo, we're going to go to the very smallest fleas in the zoological catalog that we have here of asteroids. Still, it'll be very challenging to explore an object like Eros or anything smaller in the local Earth vicinity. And why would we want to go to a near-Earth asteroid? I get asked that a lot in the talks that I give. I always envisioned, and I started working with John Lewis here back in the early 80s, and we always talked about near-Earth asteroid missions even back in the 80s as part of some larger scheme of getting people out into the inner solar system. Yes, the moon, of course. Then asteroids because they are just a little bit farther away, and then eventually expanding that capability to use the resources in space to enable us to reach Mars one day. So the reasons I would go to near-Earth objects as part of the suite of destinations that we would explore, not exclusively, but as part of the suite of destinations, would be our look into the dawn of the solar system. And these ancient objects from 4.5 billion years ago offer us a chance to see what the formation conditions of the solar system were like by collecting samples and by looking at the way these objects have evolved by collision and fracturing and fragmentation during their history. So solar system science. Second reason would be to learn more about this impacting population that we face that Bill just described. I'm having a good week. I'm here with you today and for the rest of the week. Yesterday, I was on the floor of Meteor Crater with David Kring and some graduate students that he was taking on a field walk through the crater. So we had lunch right down here at the mine site at the bottom. So this is really a pinch yourself kind of week. I loved doing this field walk yesterday with somebody who could really explain the crater's features. I hadn't been there in about 25 years. And he showed us, and I'd never remembered seeing this before, he showed us a fragment of the near-Earth asteroid that made the crater, embedded in some of the breccia and the crater walls. So that was really a thrill. And Bill, I'm going to come to that, where's Bill? I'm going to come to that conference in Flagstaff in 2013. So planetary defense. And it's not that robots can't do this job of teaching us about asteroids to protect us from them. But it's going to take a long time with robots, given the current pace that we launch robot spacecraft to asteroids and all the other competing destinations for planetary spacecraft. So if we have to have humans in deep space, we might as well learn about our enemy, if you will, and use astronauts to rapidly fill in the encyclopedia of knowledge that we need to successfully fend off a future impactor. I like this cartoon. Dinosaurs saying, now's the time to develop the technology. And we have to be smarter somehow than the dinosaurs were. Third reason I would offer about going to asteroids, and what I tell my audiences is, I love the science of going to the terrestrial planets from all the way down to the small bodies in the solar system, all the way out to an ultimate destination like Mars. And of course, we learn about the Earth along the way. But I think that the other reason to go into near-Earth space beyond the moon is to tap into the resources that are there and to make money. And I would argue with you that unless we find a way to show taxpayers that we're going to find near-term benefit, and that means wealth generation and financial improvements in our state of affairs from space, that we're never going to be able to sustain a program for 30 years to get us to a place like Mars. You've got to have an obvious and continuing benefit economically from space exploration, and particularly the human part of that, to justify that kind of commitment of treasure to getting humans all the way out to a place like Mars. So resources from space, the water that comes from clay-like meteorite samples or near-Earth asteroid parent bodies, crumbly, almost fragile bodies like Tagish Lake that were recovered up in Canada about 10 years ago. Very rich in water, 10 or 20% by weight. And so that's a great resource for human exploration or for propellant depots in space. And then, of course, you move on to metals like the nickel iron and the Canyon Diablo meteorite for construction materials. And John has written extensively about this in his book, for example, Mining the Sky. I think, what's the number, John, about each individual's net worth in terms of the nickel and iron that's in the asteroid belt? Yeah, I think you have a calculation there that says we're all worth $7 billion each because we all own a part of the nickel and iron in the asteroid belt, if we could ever learn how to tap it. Of course, what's left over after you extract the nickel and iron is even more valuable. Here's a little lump of platinum, and you know how expensive that is on the world market today. So if you could extract useful materials for space construction or propellant in orbit and then use the leftover dregs and bring them back home, some of those might be financially viable in small quantities brought back to Earth before you collapse the world platinum market. But anyway, space resources as an idea of enriching the human race, and in particular our economies, by becoming spacefaring nations. And eventually you could think of using those in-space resources to create large structures that might be able to beam power back to the Earth and so on. So that's the eventual promise half a century out. But it seems like a huge leap, but when Edison invented the light bulb, nobody imagined that 50 years after his invention that the entire world would begin, the developed world would be electrified in 50 years after his initial invention of light and generator systems. And eventually, of course, another reason for going to asteroids is to get the operations experience to enable you to go places like Mars. You can't make that big leap to Mars for the ultimate human exploration venue without having some stepping stones along the way. And asteroids can provide those literal physical stepping stones as well as the knowledge stepping stones that we need to develop the expertise and the risk reduction that we need to make any program manageable and to make a policymaker agree to spend the funds on something that he thinks will actually work and not just be a shot in the dark or a gamble. In today's risk-averse society, I think that's a very important point to show that you're making incremental progress along the way. Just to remind us of the kinds of exploration that we would do to an asteroid, here's the space station for scale. So even small asteroids like Itokawa are really daunting in terms of their size and offer a very rich exploration environment for weeks on end for a human crew to eventually do that. Here's the a small, deep space vehicle like the MPCV for scale. Okay, and you've probably all seen this graph before. I'm not going to go into it. Ask me about it later. But just what I want to emphasize is that at the small sizes of objects like Tunguska or objects like Itokawa, which fall into this range, there are tens of thousands of Itokawas out there in the Near-Earth asteroid population. For 100-meter objects, there are hundreds of thousands. And then we've got this immense pool of small objects in the Near-Earth population, but this red line shows how few we've discovered. And so there are many, many small objects that we've yet to tap into in terms of cataloging them, both from a hazard point of view and from an exploration target point of view. And some of you were at the Target NEO workshop last February in Washington, D.C., and the report that's come out of that workshop, that international workshop, was that NASA lacks the number of targets for human exploration that make a practical 2020s venture to the near-Earth asteroids doable. We don't know of enough targets that allow us to develop hardware and mission profiles that can achieve that goal. And we only know of one or two or a handful of asteroids that have the right timing and the right size and the right characteristics in terms of delta V for us to conduct a mission in the 2020s. So we have to fill in that object catalog. And the way we do that is by doing a space-based search. And one of the recommendations of a number of panels, one of the top recommendations of a number of panels that have looked at this is that one of NASA's top priorities should be a space-based search for small objects. And you would do that from that Venus trailing orbit that Bill talked about to find the near-Earth asteroids inside the Earth's orbit. That's the pink donut here. And then, of course, by lapping the Earth repeatedly in that inner orbit, you get repeat observations of asteroids to refine their orbits so you know where to find them when you want to go visit them. And then, of course, you overcome the Earth's night side limitation for ground-based telescopes by scanning this large segment of the NEO population. So Ball provided this nice figure, but it's a good illustration of the geometry advantages of going to that inner solar system orbit. And the budget to do this, we found, Rusty and I and Brian Wilcox and our other partners, Don Yeomans, in our Near-Earth Asteroid Planetary Defense Task Force last year. The budget to do this is only 1/60th of the NASA budget annually for about 10 years. Now, nobody at NASA wants to give up their 1/60th slice of the budget to fund this satellite, but it's essential that NASA somehow manage to do that, whether by seeking new OMB and congressional funding or finding some place that they could trade priorities. And it's not going to make somebody happy if they have to give that up, but only by getting all the NASA directorates. The real world that we live in today is that these directorates fight for funds amongst each other. Can we get to mounting this search, which is so important for enabling human exploration as well as looking at the near-Earth object hazard. Speaking of the hazard, Ball Aerospace has modeled a near-Earth asteroid search from space, and you get to about 90% completeness for 140-meter objects at about 8 years into the mission for a space-based telescope. And for smaller asteroids, 60 meters, you're about 50 or 60% complete at 8 years. So it does address the hazard and getting the orbit definition that we need for planning a deflection mission for the troubling asteroids out there. And then for human exploration, that same instrument delivers about 80% of the objects that are 60 meters across or bigger in just 2 years of searching. So this is really a key priority, and the Target NEO workshop stated that orbiting this telescope and getting the search underway is just as big a priority for NASA, or it should be, as developing the heavy lift launch system or the deep space crewed vehicle. And I think that's a very good judgment. That will enable us to send robotic spacecraft out to pave the way for human expeditions, and this is a concept that I worked on with NASA Ames last year. Julie Bellarose is one of my team members back there, called AMOR. It was a Discovery-class Asteroid Lander mission, which didn't get selected, but it can be refined and adapted for future NASA needs, I hope. And so those anchoring techniques are going to be all important for working on the asteroid surface. We will need a production line, I think, of asteroid rendezvous and lander missions over the next 10 to 15 years to get the knowledge we'll need in advance of a human mission. Here is a mission profile that my friend Dan Adamo, who used to be a NASA flight controller in Houston, has drawn up. And he's got many of these such profiles. This one's to 2009 OS5 in the year 2020, launching in March and recovering 6 months later in August of that year. So here's the orbit of OS5 around the sun right here. Earth is in green, and you do an Earth departure on the Orion spacecraft, and you arrive at the asteroid. You do about a 2-week exploration interval on the surface or in station-keeping formation, and then you do a departure burn and re-enter the atmosphere 6 months after you left. 6 months is nice because that's the experience base we have on the space station with the human body's medical radiation and free-fall deconditioning limitations. It's also nice in this particular mission profile, if you add up the delta V's that Dan has come up with here, it's about 5 kilometers per second to do the mission once you're in low Earth orbit to depart and then come back home. And that compares very favorably to an Apollo type, 9 kilometers per second round trip to the moon's surface and back. And that obviously is a characteristic of objects that you want to find in your catalog are those with low delta V's, Earth-like orbits for the most part. So that's just a typical kind of profile that I hope NASA will be able to find once they do a good search for potential targets. So we're going to go to a near-Earth object, and how would we carry out the exploration phase of that mission once you arrived after your multi-month trip there with some kind of a spacecraft? And would you be doing spacewalking on the surface in a spacesuit like the astronauts do on the space station, for example? Lockheed Martin came up last year with the Plymouth Rock concept, where they could do a bare bones asteroid mission with 2 docked Orion spacecraft for redundancy, and that would provide the minimal capability of just enough living space, just enough supplies to do a 6-month mission that we saw in Dan's profile. And then NASA lately has been talking in its brainstorming sessions over the last 6 months about larger spacecraft that would enable you to do more and have more margin in terms of redundancy and systems reliability to get out to a nearby asteroid. So in this concept, which I just saw this past summer that NASA shared, you've got components that have already got flight heritage cobbled together in a smart way to make a near-Earth object interplanetary spacecraft complex. You've got an Orion-type vehicle for re-entry. You've got a habitation module, maybe based on a space station node built by Alenia. Another one here as well. But docked to it is, some sort of Russian module based on their space station modules like the Zarya and Zvezda modules. Here's another re-entry module for redundancy. Maybe that's the crew taxi that you took up to the spacecraft to get on your way. And here's an orbiter, space shuttle orbiter airlock that's allowing you to do your EVAs at the asteroid. So, you've put together flight heritage that might enable you to find a more affordable pathway rather than building a ground-up, clean sheet of paper spacecraft. And I think that's a good approach for NASA to take over the next 10 years, is to identify pieces of hardware that have already been developed. We've already paid the development costs, and yet you can use those to give you a totally new capability that carries you much farther than any of these pieces would individually. Now, when you get to the asteroid, how will the human crew do that work for a couple of weeks, notionally? And when I started talking about this with my NASA friends 3 years ago, this was the idea, that you'd certainly want to go outside in a spacesuit and tramp around very lightly, of course, on the surface of an asteroid, just if not for nothing else, just to replicate the Neil, Buzz, and Mike Collins experience, having your picture taken on an alien world for the first time. But this is a really tough job to do. Without an anchoring network to enable you to crawl around on the surface, you're almost going to be in a free fall state, and it's going to be very difficult for you to do any kind of geology work standing on your fingertips for 6 or 8 hours like you do on the space station. You're going to have very limited mobility, even if you upgrade the old MMU jetpack from the 1980s. You might be able to get around, but will that have enough cold gas to get you to and from the asteroid to your cruise vehicle, and then enable you to do a full day of field work? I think that's really a big challenge. And I know how fatiguing the spacesuit is from my own experience. And yes, we'll have new spacesuits by then, but working inside any kind of inflated envelope with the limitations of that spacesuit around you is going to be fatiguing by definition. And so you'll come back in at the end of that day with your productivity falling off, and then you won't be able to go outside again and work the next day. You'll be too fatigued. You'll have to recover. And with 2 weeks at the asteroid, you're wasting time. So I think maybe you do a publicity shot like this when you arrive. Maybe not. How important is it for you to actually be seen standing on the actual asteroid itself? But maybe you evolve to, I think, something based on lunar rover concepts now called the Space Exploration Vehicle. Depending on which destination it goes to, it can be, it might have wheels, it might have rocket propulsion for asteroid work. And this SEV allows you to work in shirt sleeves. And with manipulator arms that are operated by the 1 or 2 people inside, you can spend a full day working in shirt sleeves. You can take a break for coffee and cookies, not out on the patio, but at least maybe in the back seat. And you can actually have a decent day of field work and then be ready to go and do the same thing tomorrow. And so if the spacecraft that you send to a near-Earth object has 1 or more of these vehicles on board, I think you'll have a lot more productivity when you get there. And then this same kind of vehicle has all kinds of applications at the space station and anywhere else you choose to go in the Earth-Moon system or beyond. So it's 2001: A Space Odyssey. So that's a nice thing to see that maybe science fiction might come true. But there's actually, I think, a lot of smart utility to come out of the smart design and innovation that's been going into the thinking on this lately. So the question is, though, whether NASA can actually afford to develop new space vehicles in the next 10 to 15 years. And that's a really big question mark, whether it's giant rockets or whether it's small 1 or 2 person deep space exploring vehicles like this. But we have ocean bottom experience, and we have experience field testing the lunar rover prototypes over the Constellation program's years that might enable something like this to be assembled. And it would be very important in terms of showing visible milestones to the country and to our partners to put together a vehicle like this at the space station and have it do free flights around the station, have it do maintenance on the station. If we can't afford to do and to design and build and implement something as simple as this at our own space station, then what are the prospects for sending an interplanetary vehicle right off the ground to an asteroid without any kind of testing in between. I think that's very unlikely unless you do these intermediate steps that then build support for the fact that you're actually going to go to an asteroid someday. So it's very important for NASA to use the station as an exploration test bed and try out these concepts. Some may work and some may not, but we ought to try to use that asset that we have to demonstrate our commitment to human exploration. Whether or not we actually achieve anything at the station or beyond is all driven by, in the United States at least, by the budget limitations we face. And so here's the federal budget split up in 2012 into 100 squares. And that's the allocation of resources that's in the federal budget. Almost 60% is entitlement spending. Here's national defense, about 20%. You can see education is about 3%, and NASA has half of 1%. It's about 0.6% in the most generous estimation, and it's not going up right now. So the squeeze is not coming from all these other small areas. It's coming from this, which is growing by leaps and bounds. And unless we can get our larger fiscal house in order, I don't think NASA is going to have much chance of expanding its half of a block of 1% of the federal budget. So that's the real uncertainty that I see, is whether or not we can persuade policymakers to increase the NASA share of this so that we can do deep space exploration. I think that any hope of getting out here with a flat NASA budget for 10 years is dreaming. I don't think NASA has the ultimate solution to every problem. Certainly the commercial spaceflight folks, I hope, are successful and will succeed in lowering the cost of low Earth orbit transportation. But without a recognition that it does cost more to develop reliable vehicles that can fly beyond the moon, and that we have to invest that amount over 10 years or more, we're going to go nowhere. And we can talk about Space Launch System and MPCV and Orion all we want, but because of the lack of budget planning that's in the current NASA plans, there are very few milestones in terms of when those vehicles fly. Because of that lack of structure, budget, and schedule, I have a very hard time believing that NASA can get from here to there without a change in that approach. If Bill Gerstenmaier, the head of NASA Space Ops and Exploration now, cannot draw up a schedule and get a budget commitment over 5 to 10 years to develop and field these vehicles in the next couple of years, then by 2020, we won't be anywhere close to achieving the capability that's being talked about just this past month. It's very nice to wave your hands about these designs, but you actually have to have the resources and the managerial reality to enable somebody to put together a program that can actually get there in 20 years. And that clock is ticking right now. So let me just sum up. If we're ever going to see humans at another asteroid, the budget is the driver, and that's just as important as all the technical challenges that we face. The cost over 10 years instantly becomes a topic of conversation. If you're trying to build a space launch system or an asteroid mission, people immediately trot out numbers like the $38 billion we heard over 10 years for the Orion and Space Launch System. And people say, oh my God, $38 billion in 10 years. We can never afford that, just game over, before you even start to talk about managing such a program and sustaining it. So we have to be able to sustain a program. And the way that we do that, I think, is for NASA to build a bridge to 10 years from now into the future by doing incremental things. And that starts at the space station, where we have the facilities, the power to put life support systems, put medical support systems, put transportation vehicles or exploration vehicles like that SEV into operation within 5 to 10 years, and show incrementally how we're going to develop that ability to jump off out of low Earth orbit. So NASA needs to take advantage of that facility that's already got with its partners up there. I'll go back to emphasizing that NASA has to show, not dollars in the hand in 5 years from its human spaceflight ambitions, but it should discuss how human spaceflight over the next 20 to 30 years will have a big impact on economic promise beyond Earth. And unless we can find those resources and convert them to real life benefits here for the taxpayers, I think there's very little likelihood that just the pure science draw of Mars and the asteroids is going to be sufficient to sustain a program for 30 years. So we need near-term benefits. And I think the best choice is to, all of us, when we talk to our NASA friends, is to try to motivate them towards, with their current limitations, doing the near-term doable things that are cheap, inexpensive, that can be put together in packages that then build up to 10 years from now having the capability to talk about the real asteroid mission. And one of those essential, affordable near-term steps that's so important is that space-based search system that I think a lot of the people in this room would agree upon. But we need to educate the NASA folks in charge that that's a real investment in their future that enables so many other things. So I know Rusty and I and the other members of our task force from last year have been talking to Charlie Bolden about this and trying to help him get resources from OMB. We may not be successful, but if we keep pounding on this issue, that may be the most important thing that we can do to make this a reality. So thank you for your attention, and I'll invite any questions you've got.